Hi everyone. Okay, so in this lecture we're going to talk about the full bridge inverters. For single phase. Okay. So S1, S2, S3, S4, and D1, D2, D3, D4, and this is C. This is the input VDC. Okay, so we see that here we have actually two legs instead of one leg, 1 and 2, whereas in the half bridge we had one leg. And so that's the big difference. And how we switch these determined our output voltage, which is the voltage difference between these two nodes A and B. So VAB, V out is equal to VAB. And VAB is basically determined based on whether S1 is on or S4 is on. For example, if S1 is on, node A would be connected to the positive terminal of VDC, and if S4 is on, node B would be connected to the negative terminal of VDC. Therefore, if S1, S4 is on, your VAB would be equal to positive VDC. That's the same case if you had S2 and S3 on, except that VAB would have a negative polarity of minus VDC. Okay, so the PWM in full bridge can be in two methods basically. One is bipolar and another is unipolar. Bipolar is very similar to what we explained. Its operation. It's very similar to what we explained in the half bridge. It's very close to it. So let's first explain that. PWM with bipolar voltage switch. Okay, in this scheme, the diagonally opposite switches S1, S4 and S2, S3 from the two legs are switched as switching pair 1 and 2 respectively. So what does that mean? So that means that either we are switching S1 and S4 on, so S1 and S4 turn on and off at the same time, and similarly S2 and S3 turn on and off at the same time. So you can't have a moment where S2 is on and S3 is off. So that's what we mean when we say as pair 1 and 2. So the red is pair 1 and the blue is the pair 2. So let's bring the voltage waveforms of the outputs. Okay, so picture from power electronics converter application and design. Okay, so as you can see here, when V control is higher than V triangle, so S1 is on at that time. So here S1 is on. So we said its pair has to be on too, right? So when S1 and S4 are on, what happens when we have S1 and S4 on at the same time? So B is connected to the negative terminal, S1 is connected, so VAB equals V out would equal positive VD. And when V control is less than V triangle, here we would have S2 and S3 on, and therefore we would have minus VD. So the difference that we actually see here is that before in the half bridge we had this as VD over 2 and minus VDC over 2, if you recall. So that's basically the only difference. So the operation is really very close, and the VAB1 therefore is calculated as VO1 is calculated as MA times. So before in the half bridge we had VD, now we have VDC. VDC over 2, now we have VDC. And this is for MA less than equal to 1. And if we go to overmodulation, where we have MA greater than equal to 1, or not equal, just greater than 1. Basically, the fundamental component of Vout1 is greater than VDC and then less than 4 divided by pi VDC. Yeah, okay, so this is the bipolar bipolar voltage switching, and it's very similar to the half bridge inverter that we explained, except that uh, instead of VD over square, we now have VD. So the maximum voltage that we can achieve is twice the voltage that we could achieve in actual half bridge in linear mode. Okay. Okay, now let's look at the input and output terminals of an inverter. I think it's good to look at the currents at the DC side as well. So let's say if we had an LC filter. So this is our VDC. We had a filter here. I fit that to my inverter, switch mode inverter. And at the output, there is another filter. Then the load. So this is the output, V out, and this is I out. This is another filter. So since this filter filters out the high frequency components of V out, so V out remains as a pure sinusoidal, and V out 1 basically is equal to V out, because all the high frequency components are filtered out by this filter here, and let's say it's equal to square root of 2 an RMS voltage of V out sine of omega 1t, and I out, let's say, is equal to root square of 2 I out sine of omega 1 t minus some phase angle, and this phase angle is based on whether do we have an inductive load, a capacitive load, resistive load, what load we have. Now let's look at the currents at the DC side. So the DC side current here, ID star and ID here. On the DC side LC filter, LC filter filters out the high frequency, well, high switching frequency. Component of ID. So ID here, so the high switching frequency, this filters out, and thus ID star will consist of the low frequency, which I'm going to explain what this low frequency is, what frequency exactly it is, and DC components. So now, assuming that the inverter is lossless, the instantaneous power, or the instantaneous input and output power are equal, right? So now let's write that out. P in T is equal to P out of T. Therefore, V out times ID T star T is equal to V out T I out T. So from above, from here, we can substitute for V out and I out. Okay, so now from here, if I want to find, so V out, oh sorry, this was VD, not V out. Capital VD, which is our DC input voltage, VDC basic. Yep. Okay, so if I want to find ID star, we said that it consists of a low frequency and a DC component, right? So now let's find those. At the end, we can drive ID star as V out, I out. These are the capital, so the DC, and basically the RMS, divided by VD cosine of phi minus V out, I out, divided by VD cosine of 2 omega 1t minus phi. So here, this okay, so this is the DC component, and this part is the AC component, ID2 of T. Therefore, ID, my DC component, is equal to V out, I out. These are the RMS values divided by VD cosine of phi. And then down here I have ID2 T is equal to V out, I out divided by VD times cosine of 2 omega 1t minus phi. So note that the low frequency component of ID is actually twice the frequency of the output. The of the output. So this is that low frequency that we were talking about here. And so this current would have a DC value and then a double frequency ripple on top of it. Okay, so now we explain the unipolar voltage switching for the PWM. PWM with unipolar voltage switching. Okay, in unipolar, the switches in the two legs of the full bridge inverter are not switched simultaneously, as we had in the bipolar switching. Here, the two legs are controlled separately. So before they weren't separately controlled, right? There was just one V controller and one V delta. Now they are controlled separately in this unipolar. And how are they controlled separately? By comparing V delta with VC. So until this point it's the same as the bipolar, but this is only for one leg. For the other leg, it's the V delta will be compared to minus VC, sorry, respectively. Just basically this. Okay. Okay, so let's bring the full bridge inverter topology down here again. Okay, and let's bring its voltage waveforms as well. Oops, it's not the one. Okay. Okay, so here, as you can see, when V, so here is V control, right? when V control for this is for one leg, and for leg, let's say this leg here. S1 and S2. So when V control is greater than V delta, S1 is on, and VA with respect to, let's call this point N, VA with respect to N would be equal to, so S1 is on, it's connected to the positive terminal, so it's equal to VDC. And when VC is less than V delta, so VC is this waveform here, right? So that this is the same as what we had before. Then S2 would be on, and VAN, because S2 is on, VA is connected to N, then VAN is equal to 0. So this is for the first leg, where we had basically this leg here. Right now, the control for this leg here is different. The modulation for this leg here is different, and we are comparing the same V triangle, but with minus VC. So minus VC here is this red line that I'm indicating here right now, and we're saying when minus VC is greater than V delta, then S3 is on, and VBN is equal to VDC. And when minus VC is less than V delta, S4 is on, and therefore VBN is equal to 0. Leg 1, leg 2. Okay. So based on this, you see that this kind of waveform for VAN and VBN is constructed based on comparing V control to V triangle. And as you can see, the difference is that it's right now jumping from a positive VDC to 0 now. Positive VDC to 0, whereas before in the bipolar it was to minus, from positive VDC to minus VDC. Now, based on the switching, we have four types of switching states that can happen. We can either have S1 and S4 on at the same time, or we can have S2 and S3 on at the same time. We can have S1 and S3 on at the same time, or S2 and S4. Okay, so let's write these states down here. So we have four states. First state is S1, S4 on. So V out is equal to VAB is equal to VDC. Second case was when S2 and S3 were on, and V out would equal VAB would equal minus VDC. Third case, S1, S3 on, V out equals VAB equals 0, because both VAN and VBN are equal to VDC, so their difference would be 0. And S2 and S4 are on, then Vout equals VAB equals 0. So these are the 4 states that can happen in a unipolar modulation scheme. And this picture is from the book Power Electronics. Converters. Applications and design. Okay. Now in unipolar PWM scheme, the output voltage changes between 0 and VDC, or between 0 and minus VDC. So if you go up here, so you'll see that this is the output voltage, and at each switching instant the output voltage either goes from VDC to 0, or from 0 to VDC, or it's from minus VDC to 0, and vice versa. So we don't have the VDC to minus VDC as we had in the bipolar modulation scheme anymore. So for this reason, this is called, hence the name, unipolar voltage switching. As opposed to the bipolar PWM, which the states toggled between VDC and minus VDC. Voltage switching scheme. Okay, so advantage. So what it does, the advantage, the main advantages is that it effectively doubles the switching frequency of the output harmonics. So if you look at here, you'll see that at MF of FC, which is basically our switching frequency, our FS here, we don't have any harmonics happening, and its sidebands also, the harmonics at its sidebands are also 0. And we have harmonics at 2MF plus 1 and 2MF minus 1, basically the double the switching frequency, and this makes this filtering of the high frequency components easier. Okay. So voltage jumps at each voltage jumps at each switching are reduced to VDC as compared to bipolar that was um, 2 VDC. Okay. So, and if we want to find the output, basically the first harmonic, the magnitude of the first harmonic is equal to MA times VDC. For MA less than or equal to 1, and V out 1 is between VDC and 4 pi divided by VDC for MA, basically over modulation greater than 1. Okay, so and this is it for the unipolar modulation. Now I just want to do a proof of this kind of. We use V out 1 equals MA times VDC times VDC over 2 for half bridge times VDC over 2 for and times VDC for this unipolar and bipolar. So we didn't explain why. So here in the bottom I'm gonna do that proof for of V out 1 equals MA times VDC over 2 in half bridge, and I'm gonna do that in half bridge because it's basically the baseline of all of this. So let's bring this waveform here. Okay, so here this is a magnified version of this V control and V triangle, which is here. And okay, so how do I find the VAN1, right? So VAN1 is what? VAN1 is the average of VAN over one switching cycle. Okay, so I can find it based on this. So if this is my switching cycle that starts here and ends here, right? This is TS. So this part would be DTS, which is my duty cycle, and this part, which is equal to this basically, because it would be, oh, let's just draw it there. No, it would be too messy, so I'm going to draw it here. D prime TS. So if I want to find V out ANTS as before, how do we find average? It's going to be D times, so when when I have this, V control is higher than V triangle, and thus my output V out is going to be equal to VDC over 2. So D times VDC over 2. So VDC, dVDC plus 2, and then here I have D prime, and in D prime, when I have in the D prime TS interval, I have the V triangle being greater than V control, and therefore V out would equal a minus D VDC over 2. And this can be written as D plus D prime, D minus D prime, VDC over 2, which is 2D minus 1 VDC over 2. Or to write it, I'm saying that VAN 1 is equal to 2D minus 1 VDC over 2. So before, if you recall, we said that this part, we have VAN1 is equal to MA times VDC over 2. So now I have to prove that MA is actually equal to 2D minus 1, right? So how do I do that? I take this part and magnify it here. Okay. Okay, so this is the V control. This peak is going to be V delta, which is my V of triangle. This right here is D prime TS, right? Because here we call this D prime here, TS here. And down at the bottom here, I have TS over 2. Okay, so I know that this is VC. Okay, that's V delta. Okay, so I can write from this that V delta minus VC hat divided by V delta hat is equal to D prime TS divided by TS over 2. So from here, when TS goes by TS, I can find MA is equal to VC divided by VC hat divided by V delta hat is equal to 2D minus 1 for the half bridge. And so this right here is proved.